For centuries, we believed we understood our solar system. 8 planets orbiting a single star, each one mapped, studied, and carefully placed into a predictable structure. Mercury, Venus, Earth, Mars, then the gas giants, Jupiter, Saturn, Uranus, Neptune, a complete system, or at least that's what we thought. Because in recent years, astronomers have started to notice something strange, something subtle, something that doesn't quite fit. Far beyond Neptune, in the distant darkness of the outer solar system, small icy objects are moving in ways that seem coordinated. Not random, not chaotic, but strangely aligned, which raises an uncomfortable question. What is controlling their motion? My name is FD, this is UniverseStufff, and here we explore the most fascinating questions about space and the universe. The region beyond Neptune is known as the Kuiper Belt, a vast collection of icy bodies, dwarf planets, and debris left over from the formation of the solar system. Objects here orbit the Sun at enormous distances. Some of them take hundreds or even thousands of years to complete a single orbit. Because of these long timescales, their motion is slow, subtle, difficult to observe. But over time, astronomers began tracking their orbits more precisely, and what they found was unexpected. Several of these distant objects appeared to have similar orbital alignments. Their paths through space seemed to point in roughly the same direction. This shouldn't happen. In a random system, their orbits should be scattered in all directions. But they were. They were clustered. And clustering like this usually means one thing. Something massive is influencing them. In 2016, 2 astronomers from Caltech, Konstantin Batygin and Mike Brown, proposed a bold explanation. What if there is another planet? Not a small one, not a dwarf planet like Pluto, but a massive, undiscovered world, hidden far beyond Neptune. A planet with a mass estimated to be about 5 to 10 times that of Earth, orbiting the Sun at a distance so great that it could take 10,000 to 20,000 years to complete a single orbit. A planet so distant and faint that we simply haven't seen it yet. They called it Planet 9, but if such a planet exists, why haven't we found it? And more importantly, is the evidence actually strong enough to support this idea? In the next part of our investigation, we look at the data that started it all. To understand why scientists even began considering the existence of Planet 9, we need to look more closely at the objects that first revealed the anomaly. These objects are known as extreme trans-Neptunian objects, or ETNOs. They orbit the Sun at distances far beyond Neptune. Some of them travel hundreds of astronomical units away from the Sun, where 1 astronomical unit is the distance between Earth and the Sun. At these distances, sunlight is incredibly faint. Temperatures drop to nearly absolute zero, and gravitational influences from the known planets become weaker. Which is why these objects are so important, because in such a distant region, their motion should be largely random. Yet when astronomers analyzed the orbits of several ETNOs, they found something highly unusual. Their perihelions, the points in their orbits closest to the Sun, were clustered together, and not just loosely, but within a surprisingly narrow range of angles, as if something was keeping them aligned. This alignment became even more interesting when scientists looked at the orientation of their orbits in 3-dimensional space. Not only were their closest approach points clustered, but their orbital planes were also tilted in similar ways. Imagine several objects orbiting the Sun. Instead of moving in random directions, they all seem to be following a similar pattern, almost like they are being guided or shepherded. This type of behavior is not unknown in astronomy. We see similar effects in Saturn's rings, where small moons act as gravitational shepherds, keeping ring particles confined to narrow regions. So naturally, scientists began asking, could something similar be happening here, but instead of a small moon? What if the shepherd is a planet? Badigan and Brown developed computer simulations to test this idea. They introduced a hypothetical planet into the outer solar system, a massive body orbiting far beyond Neptune. Then they simulated how such a planet would influence the orbits of distant objects over millions of years. The results were striking. The simulated objects began to show the same kind of orbital clustering observed in real data. Not only that, the simulations also predicted additional effects. Some objects would be pushed into highly tilted orbits. Others might even be forced into retrograde motion, orbiting the Sun in the opposite direction of most planets. And interestingly, astronomers have actually observed a few objects with these strange, high-inclination orbits, which raises an important question. Is this just a coincidence? Or are we seeing the gravitational signature of a hidden planet? But before we accept such an extraordinary claim, we need to consider something critical. Could this entire pattern simply be an illusion? In the next part, we examine whether the evidence for Planet 9 might be the result of observational bias rather than a real physical object. Weiter, werden wahrscheinlich mehr als 10 parts haben als beim 10 part kein Verabschiedung Mädchen sondern erst, wenn ich es sehe. Perfekt gut Entscheidung, where Mädchen es einfach so lange weiter bis das Video wirklich stark ist. Kein Abschluss bei Part 10, ich baue die Spannung weiter auf. At first glance, the evidence for Planet 9 seems compelling. Multiple distant objects, all showing similar orbital patterns, all pointing in roughly the same direction. But in science, patterns can be deceptive, because sometimes what looks like a meaningful signal is actually just the result of how we collect data. Astronomers do not observe the entire sky equally. Telescopes are pointed at specific regions. Surveys focus on certain areas more than others. And distant objects like ETNOs are extremely difficult to detect. They are faint, slow, and often only visible for short periods of time, which means that the objects we discover may not represent the true distribution of all objects out there. Instead, they may represent only the ones that were easiest to find. This is known as observational bias, and it could completely change how we interpret the data. Imagine searching for distant objects only in one part of the sky. If you only look in that region, you will naturally find objects that appear clustered there, not because they are actually clustered, but because that's where you were looking. Some scientists argue that this is exactly what may be happening with the Planet 9 data. The observed clustering could simply be the result of where telescopes have been pointed. In other words, the alignment may not be real. It may be an artifact of limited observations. To test this idea, researchers began analyzing survey data in more detail. They examined where telescopes had been looking, how sensitive they were, and what types of objects they were capable of detecting. Some studies suggested that when observational bias is taken into account, the clustering becomes less significant, less convincing, but not completely gone, which leaves us in a difficult position. The signal might be real, or it might be a statistical illusion. This is where the Planet 9 hypothesis becomes truly interesting, because it exists in a space between signal and uncertainty. On one hand, the simulations strongly suggest that a massive planet could explain the observed behavior. On the other hand, the observational data may not be complete enough to confirm that conclusion. And this is a common challenge in astronomy. We are trying to understand a system that is incredibly large, with only a small amount of available data. But there is another piece of evidence that strengthens the case for Planet 9, something that is much harder to explain through observational bias alone, because in addition to clustering, some objects in the outer solar system are doing something even stranger. They are moving in directions that shouldn't be possible under normal conditions. In the next part of our investigation, we look at these extreme orbits and what they might reveal about a hidden planet. If the clustering of distant objects was the only anomaly, scientists might have remained skeptical. After all, observational bias is a powerful effect. It can create patterns where none actually exist. But the story of Planet 9 does not end with clustering, because some objects in the outer solar system are doing something far more difficult to explain. They are orbiting the Sun in ways that should not be stable. Orbits that appear almost forbidden. One of the most famous examples is an object known as Sedna. Sedna follows an extremely elongated orbit around the Sun. At its closest point, it comes within about 76 astronomical units. But at its farthest point, it travels out to nearly 1,000 astronomical units. That's more than 30 times farther than Neptune. And here's the strange part. Sedna never comes close enough to Neptune to be significantly influenced by its gravity, which means something else must have shaped its orbit. But what? Sedna is not alone. Over time, astronomers have discovered several other objects with similarly extreme orbits. Objects like 2012 VP-113, 2015 TG-3887, and others even more distant. These objects have orbits that extend far beyond the region where the known planets can easily influence them. And yet, their orbits are not random. They share similar characteristics, similar orientations, similar distances. It's as if they were all affected by the same unseen force. This is where the Planet 9 hypothesis becomes stronger. Because while observational bias might explain clustering, it cannot easily explain the existence of these extreme detached orbits. These objects appear to have been gravitationally sculpted, but the sculptor is missing. Badigian and Brown's simulations offered a possible explanation. A distant, massive planet could slowly reshape the orbits of these objects over millions of years. Through a process known as secular perturbation, the gravitational influence of a distant planet can accumulate over time. Small effects acting continuously can eventually produce large changes in orbital shape and orientation. This is not a sudden force. It is a slow, persistent influence, a gentle but constant gravitational pull. Over time, this invisible force could push objects like Sedna into their unusual orbits. It could also maintain the alignment of other distant objects, and perhaps most importantly, it could explain something even stranger, because a few objects in the outer solar system are not just tilted. They are orbiting the Sun in completely unexpected directions. In the next part, we explore these high-inclination and retrograde orbits, and why they may be the strongest evidence yet for Planet 9. So far, we've seen patterns, clustering, extreme distances, unusual orbital shapes, but now we arrive at something even more difficult to ignore. Some objects in the outer solar system are orbiting the Sun in ways that seem almost impossible. Most planets, asteroids, and comets orbit the Sun in roughly the same plane. This plane is called the ecliptic. It represents the flattened disk of material from which the solar system originally formed. Because everything formed from the same rotating cloud of gas and dust, most objects still follow that original motion. They orbit in the same direction, with only slight variations in tilt. But not all of them. Astronomers have discovered several objects with extreme orbital inclinations. Some are tilted by more than 60 degrees relative to the ecliptic. Others go even further. A few objects appear to be orbiting the Sun in a retrograde direction. That means they are moving against the general flow of the solar system. This is incredibly unusual. Retrograde orbits are rare. And when they do occur, they are usually explained by interactions with massive planets like Jupiter. But these objects are far beyond Jupiter, far beyond Neptune, in a region where the known planets have very little influence. So how did they end up in these extreme orbits? Once again, simulations involving Planet 9 offer a possible answer. When a massive, distant planet is added to the system, something interesting happens. Over long periods of time, its gravitational influence can destabilize certain orbits. It can lift objects out of the ecliptic plane, tilt them dramatically, and in some cases, even flip their orbits entirely, turning prograde motion into retrograde motion. This process is complex. It involves long-term gravitational interactions that slowly exchange energy between objects. But the end result is clear. A hidden planet could naturally produce the kinds of extreme orbits we are observing. Without such a planet, these orbits are much harder to explain. And this is why many scientists consider these high-inclination objects to be one of the strongest pieces of evidence for Planet 9, because they represent something that goes beyond simple clustering. They suggest a dynamic influence, an ongoing gravitational force shaping the outer solar system. But if Planet 9 exists, how big is it? And where exactly is it hiding? In the next part of our investigation, we begin to narrow down its possible location. If Planet 9 exists, then it must be somewhere in the outer solar system. But the outer solar system is enormous. Beyond Neptune, distances increase rapidly. At just 100 astronomical units, the Sun already appears as a very bright star. At 500 or even 1,000 astronomical units, sunlight becomes incredibly faint. A planet at these distances would receive only a tiny fraction of the light Earth receives, which means it would be extremely difficult to see, even with powerful telescopes. But based on simulations, scientists have been able to estimate where Planet 9 might be located, not precisely, but within a general region of the sky. And what they found is both helpful and frustrating. The proposed orbit of Planet 9 is not circular, it is highly elliptical. This means the planet would spend most of its time far away from the Sun, moving slowly through deep space, only occasionally coming closer during its orbit. If the estimates are correct, Planet 9 could be located somewhere between 400 and 800 astronomical units from the Sun, possibly even farther. At that distance, it would be incredibly dim, far dimmer than Neptune, far dimmer than Pluto. Even large telescopes might struggle to detect it unless they are looking in exactly the right place. And there's another problem. We don't know exactly where along its orbit the planet currently is. It could be near its closest point, or it could be near its farthest point, which would make it even harder to find. Astronomers have been searching for Planet 9 for years. Large sky surveys have scanned wide regions of the sky, looking for faint, slow-moving objects. So far, no confirmed detection has been made, but that doesn't necessarily mean the planet isn't there. It may simply be too faint, too distant, or located in a region of the sky that hasn't been fully explored yet. Some researchers have even suggested that Planet 9 could be hiding in a particularly difficult region to observe, near the plane of the Milky Way, where dense star fields make it harder to detect faint moving objects. Others have proposed that it could be farther away than originally expected, making it even dimmer and harder to find. So the search continues. And with each new observation, astronomers refine their models, narrowing down the possible locations, trying to answer one simple question: if Planet 9 is out there, why haven't we seen it yet? In the next part, we explore the telescopes and missions that may finally reveal its existence. If Planet 9 exists, then finding it is only a matter of time. At least, that's what many astronomers believe. Because today, we have access to some of the most powerful telescopes ever built, instruments capable of detecting extremely faint objects at the edge of the solar system. But searching for Planet 9 is not like searching for a bright planet. It's more like searching for a shadow in the dark, a faint point of light moving slowly against a background of thousands of distant stars. And that movement is incredibly subtle. At such large distances, Planet 9 would move only a tiny amount over days or even weeks, which makes it difficult to distinguish from background stars. To detect it, astronomers must take images of the same region of the sky over long periods of time, then compare those images carefully, looking for anything that shifts position, even slightly. Several major surveys have already contributed to the search. Telescopes like the Subaru telescope in Hawaii have scanned large areas of the sky in high detail. Researchers use these observations to look for faint objects that could match the predicted properties of Planet 9. But perhaps the most promising tool for this search is the upcoming Vera C. Rubin Observatory. This telescope is designed to survey the entire visible sky repeatedly, over and over again, with incredible sensitivity. It will generate massive amounts of data, tracking the motion of billions of objects, including faint, distant bodies in the outer solar system. If Planet 9 is within the observable range, there's a strong chance Rubin will detect it. But the search is not only about telescopes, it's also about models. As new objects are discovered in the outer solar system, astronomers update their simulations. Each new object adds more data, more constraints, helping refine the predicted orbit of Planet 9. In some cases, new discoveries have even strengthened the case for its existence, because they continue to show similar orbital patterns, similar alignments. The more objects we find, the more the pattern becomes difficult to ignore. But there is still uncertainty, and until we actually observe the planet directly, the hypothesis remains unconfirmed. Still, the possibility remains. A massive planet, hidden in the darkness, orbiting the sun so slowly that it takes tens of thousands of years to complete a single orbit, and perhaps waiting to be discovered. But there is one final question we need to ask. If Planet 9 is real, what kind of planet is it? In the next part of our investigation, we explore what Planet 9 might actually look like. If Planet 9 exists, it is not just another small object in the outer solar system. It would be a true planet, and not a small one. Based on current models, scientists estimate that Planet 9 could have a mass between 5 and 10 times that of Earth. That places it in a category we don't currently have in our solar system. It would not be a gas giant like Jupiter or Saturn, but it would also be far larger than Earth. Instead, it would likely belong to a class of planets known as super-Earths or mini-Neptunes. Interestingly, this type of planet is actually very common in other star systems. Astronomers have discovered many exoplanets in this size range, yet our own solar system appears to be missing one, which raises another question. Was Planet 9 always part of our system, or did it come from somewhere else? If Planet 9 formed alongside the other planets, it likely originated closer to the Sun. In the early solar system, the distribution of material was much denser in the inner regions. This would have allowed a planet to grow more easily. But as the giant planets formed, especially Jupiter and Saturn, their gravitational influence may have disrupted the orbits of smaller forming planets. It's possible that Planet 9 was scattered outward during this chaotic period, pushed into a distant orbit where it remains today. Another possibility is even more dramatic. Planet 9 may not have formed in our solar system at all. It could be a captured planet, a rogue world that once orbited another star. At some point in the distant past, our sun may have passed close enough to another star system to capture one of its planets. If that happened, Planet 9 could be an alien world, a planet that formed around a different star, now orbiting ours. Regardless of its origin, the environment on Planet 9 would be extreme. At distances of hundreds of astronomical units, sunlight would be incredibly weak. The planet would be in near-permanent darkness. Surface temperatures could drop to around -200 degrees Celsius or lower. If it has an atmosphere, it would likely be composed of gases that can remain stable at very low temperatures, possibly hydrogen, helium, or even more exotic compounds. The planet might emit a small amount of internal heat, left over from its formation, or generated by radioactive decay within its core. This internal heat could create a faint glow in the infrared spectrum, which is one of the ways astronomers are trying to detect it. But visually, Planet 9 would be almost invisible, a dark, distant world, drifting slowly through the outer reaches of the solar system, a planet that has remained hidden for billions of years. And yet, its presence may already be shaping everything around it. In the next part, we explore one final possibility. What if Planet 9 doesn't exist at all? Up to this point, the Planet 9 hypothesis seems increasingly convincing. We have clustering, we have extreme orbits, we have simulations that reproduce the observed behavior, and we have a consistent explanation that ties everything together. But in science, there is always another possibility. What if Planet 9 doesn't exist at all? What if all of these observations can be explained without introducing a new planet? Because while the hypothesis is elegant, it is not the only explanation. And some scientists believe we may be looking at the problem in the wrong way. One alternative explanation suggests that the outer solar system may contain many smaller objects, rather than one large planet. Instead of a single massive body shaping the orbits of distant objects, a distributed population of smaller bodies could collectively produce similar effects. Another possibility involves the early history of the solar system. Billions of years ago, the Sun likely formed in a stellar cluster, surrounded by many other young stars. Close encounters with nearby stars could have disturbed the orbits of distant objects, pushing them into unusual configurations. Even after those stars drifted away, the altered orbits would remain, frozen in time. Some researchers also suggest that our models of the outer solar system may still be incomplete. There may be additional physical processes or interactions that we do not fully understand yet. Processes that could produce the observed patterns without requiring a hidden planet. And then there is the simplest explanation of all, that the pattern we see is not actually a pattern, but a coincidence, a statistical fluctuation in a small data set. After all, the number of known extreme trans-Neptunian objects is still relatively small. With limited data, it is always possible to see patterns that disappear as more data becomes available. This is why some scientists remain cautious, because until we directly observe Planet 9, we cannot confirm that it exists. At the same time, we also cannot rule it out, which leaves us in a fascinating position. We may be on the edge of discovering a new planet, or we may be witnessing a scientific puzzle that will lead us to a deeper understanding of how the outer solar system works. Either way, the mystery remains. But before we conclude our investigation, there is one final perspective to consider. Because if Planet 9 does exist, it would fundamentally change how we define our solar system. And in the next part, we explore what that would mean. If Planet 9 is real, then our solar system is not what we thought it was. For decades, we believed the outer boundary of the solar system was well understood. Beyond Neptune lies the Kuiper belt. Beyond that, the distant Oort cloud, a structured, layered system. But the existence of Planet 9 would change that picture completely. It would mean that our solar system extends much farther than we imagined, not just in distance, but in complexity, because a massive planet orbiting hundreds of astronomical units away would reshape the dynamics of everything beyond Neptune. It would influence the motion of distant objects, alter the structure of the Kuiper belt, and possibly even affect how comets are sent toward the inner solar system. In other words, Planet 9 would not just be another planet. It would be a key piece of the solar system's architecture. It would also raise an important question about classification. What defines a planet? In 2006, Pluto was reclassified as a dwarf planet. One of the reasons was that it had not cleared its orbit of other objects. But Planet 9, if it exists, would be massive enough to dominate its region, even at extreme distances. This would make it very different from Pluto, more similar to the major planets. Yet it would orbit in a region we have barely explored, a region that blurs the line between the planetary system and interstellar space, which challenges our definitions, our categories, and our understanding of where the solar system truly ends. But perhaps the most important implication is not about classification. It's about discovery. Because if a planet this large can remain hidden for so long, what else might we be missing? The outer solar system is vast. Much of it remains unexplored. New objects are still being discovered every year, and each discovery adds another piece to the puzzle. Planet 9 represents something deeper than just a potential new planet. It represents the idea that even in our own cosmic neighborhood, there are still unknowns, still mysteries waiting to be uncovered, and perhaps somewhere in the darkness beyond Neptune, a distant planet is still orbiting quietly, unseen, undetected, but not entirely invisible, because its presence may already be written into the motion of everything around it. At this point, the question is no longer just theoretical. If Planet 9 exists, how close are we to actually finding it? Because for the first time in history, we have the technology capable of scanning the sky in unprecedented detail. And the search is no longer random. It is targeted, guided by models, refined by data. Astronomers now have estimated regions where Planet 9 is more likely to be located. They know approximately how bright it might be, how fast it should move, and what kind of signal it would produce in telescope images. This means we are no longer searching blindly. We are narrowing in, slowly, carefully, systematically. The next few years may be critical. The Vera C. Rubin Observatory, once fully operational, will begin a survey known as the Legacy Survey of Space and Time. This survey will repeatedly scan the entire southern sky, every few nights, for 10 years, tracking changes over time, detecting motion, capturing objects that would otherwise go unnoticed. If Planet 9 is within its observable range, this telescope may find it, but even if it doesn't, the data it collects will still be incredibly valuable, because it will either reveal new distant objects that strengthen the case, or provide enough data to rule the hypothesis out. Either outcome is important, because science moves forward not just by discovery, but by elimination. There is also another possibility, that we may not find Planet 9 directly, but instead confirm its existence indirectly, through its gravitational effects, similar to how Neptune was discovered. Before Neptune was ever seen, astronomers noticed irregularities in the orbit of Uranus. Those irregularities pointed to the existence of an unseen planet. And eventually, Neptune was found exactly where the calculations predicted. Planet 9 could follow a similar path, its presence inferred through motion, through patterns, through the subtle shifts in the outer solar system, until one day, we finally see it, a faint point of light, moving slowly across the sky, confirming that something massive has been there all along. But until that moment, we are left with a mystery and one final question, not just whether Planet 9 exists, but what it says about how we explore the universe. In the next part, we bring everything together. The search for Planet 9 is not just about finding a missing planet. It is about understanding the limits of our knowledge. For centuries, humanity believed the solar system was complete. Each planet discovered, mapped, and placed into a predictable structure. From Mercury to Neptune, a finished system. But history has shown us something important. Every time we think we understand the universe, we discover something new that changes the picture. Uranus was once unknown. Neptune was predicted before it was seen. Pluto was discovered, then reclassified. And now, we are once again faced with the possibility that something large, something significant, has been hiding in plain sight. What makes Planet 9 so fascinating is not just the idea of another planet. It's the method of discovery. We are not seeing it directly. We are inferring its existence from its influence, from patterns in motion, from gravitational fingerprints left behind in the orbits of distant objects. This is how much of modern astronomy works. We often cannot see things directly. Instead, we observe how they affect their surroundings. Black holes, dark matter, exoplanets, and now, possibly, Planet 9. This approach requires patience, careful analysis, and a willingness to accept uncertainty, because sometimes the evidence is incomplete and the answer is not immediately clear. So where does that leave us? Right now, Planet 9 exists as a hypothesis, a strong one, supported by simulations, supported by patterns in the data, but not yet confirmed. It may be out there, orbiting slowly in the distant darkness, or it may not exist at all. And the patterns we see may lead us to an entirely different discovery. Either way, we are learning something new about the outer solar system, about its structure, its history, and its hidden complexity. And that may be the most important part of this entire investigation, because even in our own solar system, we are still exploring, still discovering, still asking questions, and somewhere far beyond Neptune, the answer may already be waiting, unseen but not undiscovered. Let's imagine for a moment that Planet 9 is real, and that one day a telescope finally detects it, a faint point of light, moving slowly across the sky. At first, it would just be another candidate, another distant object. But over time, as its motion is tracked and its orbit calculated, the realization would begin to set in. This is not just another icy body, not just another dwarf planet, but something much larger. something massive enough to reshape our understanding of the solar system. The confirmation would not happen instantly. It would take weeks, months, perhaps even years of observation. Multiple telescopes would need to verify the discovery. Independent teams would analyze the data, and only then would the announcement be made. The discovery of Planet 9 would be one of the most important events in modern astronomy, because it would be the first new major planet discovered in over 150 years. Since Neptune in 1846, it would immediately become a priority for further study. Astronomers would begin analyzing its brightness, its spectrum, its temperature, trying to understand what kind of world it is. Is it an ice giant, a super-Earth, a captured rogue planet? New models would be developed. Old models would be revised. And suddenly, the outer solar system would feel much less empty, because instead of a distant void beyond Neptune, there would be a massive planet quietly orbiting in the darkness, and eventually the next step would become unavoidable: exploration, because once we know where Planet 9 is, the question becomes, can we go there? Reaching such a distant planet would be extremely difficult. Even with current technology, a mission could take decades, possibly longer. But humanity has sent spacecraft to Pluto, to the edge of the solar system, and beyond. So the idea is not impossible. A future mission could be designed to study Planet 9 up close, to photograph its surface, to analyze its atmosphere, to understand its origin. It would be one of the longest journeys ever attempted, but also one of the most rewarding, because for the first time, we would be visiting a world that remained hidden for billions of years, a planet that we didn't even know existed, until we followed the clues left behind in the motion of distant objects. At the beginning of this journey, we asked a simple question: is there a hidden planet in our solar system? Now, after examining the evidence, the simulations, the alternative explanations, and the ongoing search, the answer is still not completely clear. And that is exactly what makes this mystery so compelling, because Planet 9 exists at the edge of what we know, not confirmed, not disproven, balanced between possibility and uncertainty. It is a reminder that even in a system we have studied for centuries, there are still gaps, still unknowns, still questions waiting to be answered. But perhaps the most interesting part of this story is not whether Planet 9 exists, it's how we are trying to find it. We are not simply looking through a telescope and hoping to see something. We are using physics, mathematics, patterns. We are reading the motion of distant objects like clues in a puzzle, inferring the presence of something we cannot yet see. This is how science often works. We detect the invisible by observing its effects, just as we do with black holes, with dark matter, with distant exoplanets, and now, possibly with a planet in our own solar system. So where does that leave us? Somewhere in the outer darkness, beyond Neptune. There may be a planet, a massive world moving slowly through space, completing an orbit that takes thousands of years, or perhaps there is no planet at all, and the patterns we see will lead us to a different discovery, a deeper understanding of how planetary systems evolve. Either way, the search itself is the discovery, because it pushes us to look farther, to question more, to explore what lies beyond the boundaries we thought we understood. And maybe, one day, we will finally look into the darkness and see it, a new planet or a new answer waiting for us all along. What do you think? Is Planet 9 really out there? A massive, unseen world shaping the outer solar system? Or just a pattern we don't fully understand yet? Because right now we are standing at a very interesting point in science. We have enough evidence to ask the question, but not enough to answer it. And that's exactly where discovery begins. If you enjoyed this investigation into one of the biggest mysteries of our solar system, make sure to let me know. Which theory do you find most convincing? A hidden planet or something else entirely? And if you want to explore more mysteries like this, from interstellar objects to black holes and beyond, you're in the right place. My name is FD, this is UniverseStufff, and here we explore the most fascinating questions about space and the universe. If you enjoyed the video, feel free to like and subscribe. It really helps the channel grow. And I'll see you in the next journey. Until then, keep looking up.